My name is Freddy Soria. Thank you very much once again, Chair, and everyone who's listening to this presentation. I'm coming from the Universidad Católica Boliviana in La Paz. We are trying to set up a research center in water and energy. As you can imagine, the topics are very wide. And today I'm going to present some application of a couple of models, well-known models in water energy nexus, in order to assess potential climate change impacts in hydropower generation in La Paz, Bolivia. Our region is located in the tropics, so our study area is in some Andean watersheds, and our scope, well, as part of my conserve water energy nexus with WIP and LEAP models could be a good alternative to try to answer some concerns we have in the region, and we have in the country as well, applied to the Andean cities of La Paz and El Alto. Our population is about 1.8 million people in both cities, so you can imagine how relevant this issue is for us. My presentation might be a little bit slow. My apologies for this. So about the study area and problematic, well, let me share with you some pictures on that, so you can imagine how heterogeneous our geographic location is. Our interest in this is try to raise awareness on potential climate change impacts on hydropower generation in mountainous Andean watersheds, where the Andes goes far from the south in our continent up to the north. It crosses Chile, part of Argentina, perhaps Bolivia, Peru, Ecuador, and goes up to Colombia, where the last presenter has placed his work. So it's a very beautiful scenario, as many scenarios in our beautiful world. But our interest is not only to focus, perhaps in the near future, only in my country, but also in other places where they may have these kind of issues. On the top picture, you can see how the Andes interrupt our scenario, and in the lower picture, you can see how the Andes travel downstream as it crosses the headwaters of the Amazon River basin. So that's our scenario. Well, I can change to my next presentation, next slide, sorry. Well, glaciers in this region have lost in average more than 30% of their surface in the 1980s. So just in the last decade, awareness has been right, because that kind of behavior was going to bring some negative things to our area. So if I bring GCM data, for example, that data suggests an average increase in 2 degrees, which from our perspective is too high, and the glaciers have felt that in the same way. What are the impacts are predicted by those GCMs? Possible precipitation reduction, for example, and of course that will impact as well our beautiful and viable glaciers. The picture I'm showing you in this slide is part of the upper part of the system, which I will explain in the next slide. This is a dam located above 4,000 meters above sea level, and the system goes down in a cascade-like scheme up to reaching about 300 meters above sea level. So there's more than 3,000 meters between the upper part of the system and the lower part of the system. In the upper part, as you can see, is a dry area located near the Altiplano Plateau, and the river crosses down very interesting ecosystems like rainforest, as I showed you, the glacier area, and it goes down until it flows to the Amazon River basin. In our country, hydropower is not the main source for electricity generation. 74% of electricity generation is produced by thermoelectric plants. Our concern is that those plants are fueled by natural gas. Well, our gas is going to end up perhaps in the next decade. And at this time, 25% of the electricity consumed in Bolivia is generated by hydropower. That's why our interest is in this topic. Well, telling you about the Zongo system, which is part of our study, it is important for hydropower generation, of course. As I said, more than 25% in the countries produced in a couple of systems like this. This is the biggest one. Once again, as I said, the cascade scheme goes and crosses a very rich ecosystem. And our issue is that, as you can imagine, an important part of the system, at least the two upper parts, the two components in the upper side of our system, is fed by glacier melt. So rising temperatures and an increase in glacier ablation and glacier loss. So it has to affect glacier melt. And as it affects, since, for example, this depth is mostly fed by glacier melt, so it will affect sometime in the future to our hydropower generation as well. So hydropower generation affected, thermoelectric plants, power plants affected. So the future might be something we have to think about. Let me explain you in simple words what the water energy nexus is, at least for this study, how we have set up the models and the way of thinking in order to apply the models I have used. Well, I have me and my student. Of course, my student couldn't be here for presentation. He's already working some other place, so I'm in charge. Commonly considered nexus are like this. Hydropower plants are in the upstream part of the watershed, right? So as rivers flow downstream and water is used for drinking water supply, for example, agriculture, and all those water uses that can come up. In our case, we don't have that kind of relationship. For example, I'm sure you cannot see my arrow, but the situation is like this. Let's start with those systems with the green arrow. Those small triangles, blue triangles, are the Zongo hydropower plant system, and on the lower part of my image are the second hydropower plant system that feeds the country in terms of electricity generation. Well, as you can see, the Zongo hydropower plants are the biggest. Today, the Miguillas and Cholla hydropower plants are not working at full because, I don't know, there is some administrative issues, I think. And in terms of water supply and the direction of natural flow from our rivers, I have two systems very different. On the north east side are the systems which feed directly to rivers, which later in Brazil will join the Amazon River basin. But with the sky blue arrows, I'm showing you other system which part flows to the Amazon River basin and the other part to the left to the west will flow to the Titicaca Basin. Titicaca is one of the most important sceneries for touristics and, of course, environmental value. In case of our setup, as I said, the Zongo system is very simple. Zongo system does not supply drinking water to La Paz, so the nexus we have set up is like this. Zongo Basin only provides water for hydropower generation. Hydropower fed at least in 2/3 of the basin approximately is fed by glaciers, glacier melt. So our setup is likely to be affected by climate change. That's our idea. Quite simple. Now, let me explain you a little bit in 1 minute how climate change is potentially affected and impacting our Zongo system. As I said, Zongo Dam, which is the one I've been showing you in the photos, is above 4,000 meters above sea level, with some contributors, at least most of them, coming from glacier melt. Well, climate change strikes that part of the system. On the middle part of the system, there are some other reservoirs whose name I'm not going to tell you because it's difficult to pronounce it perhaps in English. The latter is fed as well by small glaciers. And in the lower part, there's the forest, the semi-tropical area, where, yeah, there are minimum glacier melt contributions, but the impacts expected would be the changes in temperature, precipitation, the changes in land use, I mean, the cultivations, the old cultivations of fruits, for example, is getting lost because of some other kind of production that the former government used to support, but I'm not going to say anything about political issues because I get sad. According to model calibration, I'll go into the result part. We have used two models, as I said, WIP, which is focused on water, and LEAP, which is focused on energy planning. I'm not going to show you the details of calibration, of course, because of time. WIP calibration, one example on the lower part of this, of the basin, whose headwaters is presented in the picture, which I like a lot. Calibration has been carried at the outlet of the Zongo Basin. Two partially glaciarized basins as well have been calibrated with the model as well, and two additional stations in the La Paz watershed. Some colleagues from a Swedish institute, I have forgotten, SEI, responsible of the WIP calibration, have helped us with the calibration, have shared with us the data. So we have had to only to extend the temporal application. It has been a big issue, and we are always thankful for our colleagues who shared their work with us. In terms of LEAP, the calibration, it's a little bit different because the data is more scarce. Calibration is demand-driven as the model itself, and it has been carried only with the total electricity consumed in the cities. We don't have data specific for each of the energy plants, for example. I don't have the energy spent by the two thermoelectric, but we have to have some inner calculations in order to try to estimate that. So that's how we have worked. From the modeling approach, the perspective has been very simple. To highlight the role of water energy nexus modeling perspective, we have considered two approaches. First, where hydropower generation has been modeled only using LEAP, and the other perspective was to try to model hydropower generation and, of course, all the aspects which affect that from the WIP-LEAP nexus perspective. And of course, for both views, the HEP GCM model outputs have been used from the RCP 8.5. We wanted to assume the worst possible conditions, and that's why we have used that GCM model. according to results, is perhaps something you have expected. For example, on the upper left figure, it's only the perspective from the LEAP model. I mean, only from energy, no water inside that scheme. The trends are very simple. They simply describe the behavior of electricity supply demand data. But when we apply the WIPLIP perspective, I mean energy and watershed, the perspective seems to be more realistic because it reflects the dependence on watershed runoff generation trends and variability, of course. But why is it concerning to us, and why is it concerning to our country, and perhaps to other countries in the region, which may have similar schemes for electricity generation, for example? Of course, in our case, we have identified that at the time supply capacity is surpassed, which occurs about 2013. You might find as well some break in the trend because of some administrative changes in terms of electricity generation. Well, that's an issue, right? Because at that time there's the possibility that the managers of the system had to borrow energy from thermoelectric plants, which is fueled by natural gas, which in turn is a key export product in our country. We live basically from natural gas we have lived during the last 2 decades, perhaps, which in turn is likely to finish soon. I'm not going to tell you when, but soon in the future, according to the expectations of the experts. I'm not an expert in natural gas, but that's a big issue. That's why it is concerning to us. So that takes me directly to the conclusions to finish with my presentation. Well, we believe more realistic, of course, has to be, but perhaps from a planning perspective that hasn't been considered. So once again, my main concern and our concern from the group have been working on this is what will occur when gas disappears. I mean, no gas, no glaciers. So how are we going to fuel all our system for electricity purpose? Well, recommendations for planners are very straightforward. Well, a hydropower system relying on a resource which is sensitive to potential climate change impacts should, as possible, be considered within a nexus perspective rather than from isolated perspectives. As you can see, the recommendations are very straightforward. The results are very straightforward. Are kind of expected results, but at least from our perspective, that's something that hasn't been considered, at least from a planning perspective. Something expected, not considered. So let's see what the future expects. Thank you very much, Chair. And thanks to anyone.